This video explains how to analyze PostgreSQL query execution plans using explain and explain analyze. I create a users table. The ID is serial, which is an auto-incrementing integer. Primary key adds a unique constraint and an index. Username has a maximum of 50 characters. Next, I create a posts table. It has an ID, a user ID reference, and a title with 200 character limit. I insert 10,000 users. Each username is the word user followed by a number. I insert 50,000 posts. Each post references a random user ID. Each title is the word title followed by a number. Now I test a simple query. Find the user with username user1. I add explain before the query. This shows the execution plan PostgreSQL will use without actually running it. PostgreSQL returns its predicted execution plan. This shows how it will execute the query and estimates the cost. Sequential scan checks every row. Cost 0.00 to return the first row. Cost 180 to scan all rows. It expects to find one row that is 12 bytes wide. The filter shows the condition. It compares username against the literal string user1. Both are cast to text for comparison. This plan is expected. Without an index on username, PostgreSQL must scan every row. The width estimate is reasonable for a varchar 50 column. Explain Analyze actually runs the query and shows what happened. This gives real timing data, not just estimates. It uses sequential scan, cost 0.00 to find the first row, cost 180 to scan all. Found one row of 12 bytes. Took 0.012 milliseconds to find the first row. Took 0.012 milliseconds to find the first row. Found one row in one loop. The filter compared username to user1, both cast to text. It removed 9999 rows. Planning took 0.041 milliseconds. Execution took 0.626 milliseconds. It checked all 10,000 rows. Sequential scan doesn't scale well as the table grows. I can improve this with an index. I create an index on username. This should speed up lookups on this column. Now I run the same query with explain analyze again. It uses an index scan with the new index. Comparison shows cost increased slightly from 0 to 0.29 for first row, but execution cost dropped to 8.30. Execution time dropped to 0.041 milliseconds. No rows filtered out, it found the row directly. This changes time complexity from O of n to O of log n. Sequential scan is linear time. Index scan uses a B-tree structure for logarithmic time. Now I test a join query. Get user1 and their posts. I only want username and title in the response. The join produces multiple operations, not just one scan. Let me walk through each step. Step 1. It does index scan to find user1. Cost 8.30. Time 0.025 milliseconds. Step 2. Build a hash table from user1 for the join. Uses 9 kilobytes of memory. Step 3. Sequential scan all posts to find ones that match user1. Cost 819, time 2.290 milliseconds. This is slow. Step 4. Hash join combines posts with user using the hash table. Time 4.832 milliseconds total. The sequential scan on posts is the bottleneck. I can speed this up with an index. I create an index on user ID in the posts table. This should speed up lookups by user. Major improvement. Cost dropped to 30.87. Execution time dropped to 0.076 milliseconds. No more scanning all posts. Hash join changed to nested loop. Uses new index. Bitmap heap scan gets row values. Now I test a range query. Find posts where user ID is less than 100. This should return relatively few rows. It uses the index to find matching posts. Then bitmap heap scan gets the values. Same strategy as the exact match. When result set is small, indexes help. Now I increase the range. User ID less than 5,000. This returns about half the table. Indexes become less useful when results are large. PostgreSQL switched to sequential scan. It ignores the index. This is smart. When you want half the table, scanning directly is faster than using an index. Indexes help when you find 1 in a million. They do not help when you want 500,000 in a million. PostgreSQL switches to sequential scan when you request more than 5 to 15% of rows. Let me test the threshold. User ID less than 500 is about 5% of the table. It still uses the index at 5%. We are just below the threshold. Any larger and it would switch to sequential scan. Now I test a composite condition. Find post where user ID is 1 and title starts with title 1. It uses the user ID index first, then filters by title with a like pattern. It finds candidates by user ID first, then checks the like condition. This is not optimal. I create a composite index on title and user ID. Let me run the same query again. One step only, major improvement. It uses the new composite index. Both conditions are in the index condition now. Note that leading wildcards like %title do not work with indexes. Index column order matters. Think of it like layers. This index is title, then user IDE. Good if you filter by title first. Not good if you filter by user IDE alone. I create another composite index. This one is user ID, then title. Better order for my query pattern. PostgreSQL picks the better ordered index. Execution time improved slightly. This video covered how to diagnose query performance using explain and explain analyze. Indexes help when finding small result sets in large tables. PostgreSQL automatically chooses the best strategy based on query patterns.